the title has been already announced. I should say that this is it's based on a joint work with Silvana Avramska-Lukarska and her Dr. Vater, Dirk Hundertmark from Karlsruhe. And so let me start with the basic setup of the problem that we are looking at. The basic object of our interest is a magnetic Schrödinger operator, which is formally given by this expression, where P is a momentum operator, is minus I times nabla, and V is a scalar field on Rn, is electric potential, plays the role of the electric potential, and A is the magnetic vector potential, which generates a magnetic field via the usual identity, the rotor A is equal to B. Now recall in Rn, B can be identified with an antisymmetric matrix. In R2, it can be identified with a scalar field, and in R3 with a vector field. Anyway, throughout, we will always work under the tacit conditions that both B and V are vanishing at infinity. And it turns out that under these conditions, the essential spectrum of this operator covers the positive half-line from 0 to infinity. Okay. Note that it is not required that A goes to 0, but what is sufficient is that the B, the magnetic field generated by A, goes to 0. Okay, so and the main question that we address is under which conditions on both magnetic and electric field can we exclude the presence of positive eigenvalues? In other words, of eigenvalues embedded in the essential spectrum of the operator, or more in general, if we cannot exclude presence of all eigenvalues or positive eigenvalues, if we can exclude presence of eigenvalues above certain positive energy level, which above certain threshold, which we denote by lambda, capital lambda, and which is a point in the essential spectrum. Okay. There is, of course, a bit confusion might be a confusion in the notation that I call the operator HAV, but I only want to give conditions on B because we know that the spectrum is gauge invariant. Of course, the operator does depend on A, but the spectrum in general and the eigenvalues in particular depend only on the magnetic field B. So all the assumptions that we will talk about will only be given on the magnetic field B, because I want, of course, the results to be gauge invariant. Okay. Now we are, of course, not the first ones who look at this problem. So let me say very briefly, something about the history. And the history is quite long of this problem. It goes back as far as to a pioneering paper by Kato in 1959. So the major part of the papers which I'm reviewing refer to the situation without magnetic field. So A is 0, so B is 0. Okay, so Kato in his landmark paper proved that the non-magnetic Schrödinger operator in Rn has no positive eigenvalues if the potential is continuous, and most of all, the most important condition of Kato is this one, that V at infinity is a little o of 1 over x, okay? So if V decays just faster than 1 over x, then we can exclude, then Cato says that this excludes the existence of any positive eigenvalue. Right. This result of Cato was later improved and extended by Simon and Agmon, who considered Schrödinger operators again without magnetic field, but with electric field that can be decomposed outside a compact set into a sum V1 plus V2, where the first one still obeys the condition of Cato, which means is a little o of 1 over x. But the second one can be can be considerably more long range. It is only required that it goes to 0, and it is required that the lim sup of the x times grad v2 is finite. Okay, so this puts some bound on the possible oscillations of this, and this quantity lim sup x dot grad of v2, we call it omega 0, and Simon in his paper proved that in R3 such an operator cannot have eigenvalues above this omega 0. Okay, so this is clearly an extension of Cato, because of course you can split the potential as you want. So if you put V2 equal to 0, then you reproduce the result of Cato, of course. Okay, but the point is that you can apply this condition also on potentials that do not obey this condition of Cato, but where you have one part which is short range and the other part which is long range, and from this long range part you will get the threshold of this type. And this was later improved by Agmon, who extended it to all dimensions and who lowered this threshold obtained by Simon by dividing it by 2. Of course, the lower the threshold, the more precise the result is. So Agmon excluded eigenvalues, all eigenvalues above omega 0 half. Okay. Now, these conditions, first of all, the condition of Cato is basically optimal, is essentially optimal, because it is well known, and from a very, very old paper by Wigner von Neumann, that in dimension 3 there are potentials, for instance, which produce positive eigenvalues embedded in the essential spectrum. And the example of this potential is written here explicitly. So this is the example by Wigner von Neumann. And this potential creates eigenvalue 1. Okay, so if you add to the Laplacian this potential V, which is a radial potential, then the resulting operator will have eigenvalue 1. And if you look at this potential V, there is this function g of r, but when r goes to infinity, you can think of g of r basically like r or 2r. Yeah. So you have r in the denominator, you have something which goes like r to the power 4. And in the numerator, you have 3 terms. They are of course oscillating, but the amplitude of the first term is g to the power 3, which goes like r to the power 3. So this first term does not, if divided by the denominator, does not obey the condition of Cato. It's not small o of 1 over r, it's only capital O of 1 over r. Whereas the rest fulfills the condition of Cato, because it is capital O of 1 over r squared. So the natural splitting in this case would be that you take this first term as V1 and the rest as V2. And if you do so, then it turns out that your omega 0, which is the threshold, is equal to 16. Okay, so in this case, the result of Simon says that there are no eigenvalues larger than 16, and the result of Agmon says that there are no eigenvalues larger than 8, whereas we know that there is eigenvalue 1. But from the point of view of decay condition, it also says that the condition of Kato is essentially optimal, because if you replace small o by a capital O, then you can have eigenvalues embedded in the essential spectrum, positive eigenvalues. Okay. Then these results have been then further extended and improved. There is a series of papers by Fröse-Herbst and Fröse-Herbst, Hoffmann-Ostenhoff, and Hoffmann-Ostenhoff, who used an idea of weighted commutator estimates. I will talk about them later, and also extended this to many-body operators. And this allowed them to relax the conditions on the electric field. And other generalizations can be found in this paper by Jerison, Koenig, Ionescu, and Jerison, and Koch and Tataru, who used Kahneman estimates, and they really extended those results to very rough electric potentials. However, much less is known about the operators with magnetic field, and in particular in dimension 2. Some of the previous results, mainly by Koch and Tataru, can be applied also to magnetic Schrödinger operators, but first of all, they are not gauge invariant, and second of all, in dimension 2, they are only applicable to magnetic fields with zero flux, which means with zero integral over R2. Only recently appeared a paper by Fanelik, Rejcicek, and Vega in 2018, where the authors gave sufficient conditions, but not for the absence of embedded eigenvalues, but for the absence of all eigenvalues of the Schrödinger operator in dimension 2. But this is not the question that we address. We are addressing the question of absence of embedded eigenvalues, which means in our case positive eigenvalues, allowing for possible discrete negative eigenvalues. So let me now jump into our assumptions. As I already said, the magnetic field in general in Rn can be identified with an antisymmetric matrix valued function. And the object that will be very important for us is this vector field B tilde, which is defined, which is connected to the magnetic field through this equation. So B tilde is just a normal vector field in Rn. And for instance, if the dimension is equal to 3, then the magnetic field, as I said, can be identified with a vector field. You just take, because if the dimension is 3, then this matrix BJK is a 3 by 3 matrix, but it's antisymmetric. Okay, so you only have three independent elements of the matrix: B32, B13, and B21. So this can be identified with a vector field. And in this case, this vector field B tilde is just a vector product between this vector field and X. Okay. And our assumptions on the magnetic field can be formulated via this vector potential B tilde. We assume that it is LP locally with P which is larger than the dimension. And as for the behavior at infinity, we assume that B tilde is bounded at infinity. Okay. So this morally, this means since B tilde is given by sort of a product of a magnetic field and X, so this is the decay condition. This morally is almost the same as assuming that the magnetic field at infinity decays at least as 1 over X. Okay. So these are the assumptions. So assumption 1 is the only assumption on the magnetic field. Now I say that it is a pointwise version of the assumption because in the paper we also have a much weaker assumption via the quadratic form, but it would take a long time to formulate it. So for the purpose of this talk, I will only talk about the pointwise assumption. Now, as far as the electric field is concerned, we will put the similar assumptions as those in the papers by Simon and Cato. So we have some local regularity assumption on V, and we assume that outside some compact set, V allows a splitting decomposition V1 plus V2, where V1 is a continuous function and V2 is a C1 function on the complement of this compact set. Yeah. So let's say at infinity we have this splitting. We assume that both V1 and V2 tend to 0, so that there's no cancellation between those two. So of course the potential goes to 0. And we assume that V1 times X is bounded at infinity, and that this radial derivative of V2, so X dot grad V2, is bounded as well at infinity in the complement of this compact set. Okay, so these are our assumption on the magnetic and electric field. Now, let me say a few words about the gauge. I already said that we want the results to be gauge invariant. However, the proof is, and the technique of the proof is not gauge invariant at all. And from the very beginning, we fix a concrete gauge, which is the Poincaré gauge. The Poincaré gauge is given by this blue equation. So A of X is just the integral from 0 to 1 of B tilde t times X in dt. Okay, so one can check rather easily, at least if B is regular enough that the rotor of this A then coincides with B. And moreover, under our regularity assumptions on B, one can show that this vector field is in L2 locally. Okay, L2 locally, which allows us to define the operator, the differential operator which we work with, in the usual way via a closed quadratic form, which is this one, QAV. So this is the magnetic gradient, the L2 norm squared of the magnetic gradient, and plus then we have the potential energy, and the form domain is the usual magnetic magnetic Sobolev space. So this is the domain of this operator P minus A, which consists of all L2 functions for which P minus A applied of U is an L2. Okay. One important thing, one important property of the Poincaré gauge is this one. It's that this vector potential is perpendicular to X on the whole Rn. Okay, and this is very useful, and it is used in our proof in many places. All right. So from now on, the gauge will not change. We will always work with this Poincaré gauge. All right. So let me formulate now the main result with this pointwise version of the assumptions. So under the stated assumptions, which I mean the 1, 2, 3, 4 here, under these assumptions, the Schroedinger operator in Rn has no eigenvalues above this threshold lambda, where the threshold lambda depends on 3 quantities: beta, omega 1, and the omega 0. Okay, so omega 0 is the same as it was in the paper by Simon and Agmon. Omega 0 is this. So we have a splitting V, we decompose V into a sum V1 plus V2. And omega 0 is the same as before. Omega 1 is the lim sup of x times V, V1, of course, norm of x times V1, which is finite due to our assumptions. And beta is the lim sup of the absolute value of the, of the norm of a vector field B tilde. Okay, so beta, omega 1 and omega 0 are three positive quantities. And as expected, since we are talking about positive eigenvalues which are embedded in the essential spectrum, the threshold only depends on the behavior of B and V at infinity. There is no, apart from the regularity assumptions which allow us to define the operator, there are no assumptions on the local behavior, and in particular no bounds, no global bounds on B and V. All what matters for the absence of eigenvalues of all eigenvalues, or absence of eigenvalues above certain threshold, is how the electric and magnetic field behave at infinity. And the threshold is then constructed via these three quantities. Okay. So if we want to find a connection with the previous works that I have cited on one of my previous slides, we can see that if the magnetic field decays faster than 1 over x, then beta is of course 0, because in that case B tilde tends to 0. And if I now use the splitting, if I put everything on the component V1, okay, so if the potential is regular enough, okay, I can split the potential V as I wish, of course. Yeah. So if I put everything on V1 and 0 on V2, then I get lambda equal to omega 1 squared. And in this case, I get an extension of the result of Kato to magnetic Schrödinger operators, because Kato says that if omega 1 is equal to 0, this is exactly the Kato condition. Yeah, Kato says that if V is a small o of 1 over x, then x times V goes to 0. So omega 1 would be 0. Then I have no positive eigenvalues. And so this extends this into the situation when x times V does not go to 0, but remains only bounded, and also to a situation where we add a magnetic field which vanishes sufficiently fast at infinity. The other way around, if I use the splitting V1 equal to 0 and V2 equal to V, then lambda will be omega 0 over 2, and this extends the result of Agmon and Simon. Okay. Extends in the sense that it also includes magnetic fields. Okay. Now, so I have already talked about the optimality of the decay conditions of the electric field in the papers by Kato, Agmon, and Simon, and the ones that followed them. I have said that this decay assumption is essentially optimal in view of the well-known example of Wigner von Neumann. Now the question is whether also the decay condition on the magnetic field, which is new in this result, is optimal. So I recall that the decay assumption of the magnetic field is that the magnetic field itself decays at least as fast as 1 over x. Okay, under this condition, the B tilde remains bounded at infinity, and beta, and this means that beta is finite. So whether this is optimal or not. So for this one, we would need to compare the results with some example in which we have embedded eigenvalues for Schrödinger operators with magnetic field. And the example exists, is very well known. Is by example is by Miller and Simon from 1980. And it turns out that it is in fact in some way much simpler to create embedded eigenvalues for magnetic potential, for magnetic Schrödinger operators than those without magnetic field. And the example goes as follows. So the example is two-dimensional. Miller and Simon considered magnetic Schrödinger operators in dimension 2 without any electric field, and with a magnetic field which is radial. Okay, so it can be identified with the function small b of r, where r is the is the norm of x. And what they showed is that the spectral properties. I'm sorry, there is a misprint here. It should be HA0, not HB. Okay, this is a misprint. That the spectral properties of the resulting Hamiltonian depend very much on how fast the magnetic field decays to zero at infinity. In particular, they show that if the magnetic field decays faster than 1 over r, still with the power, but with the power which is bigger than 1, then the spectrum is purely absolutely continuous. On the other hand, if the magnetic field decays slower than 1 over r as a power 1 over r to the power alpha, with alpha smaller than 1, plus some reminder terms, then the whole spectrum is dense pure point. So there's no absolutely continuous spectrum in that case. And most interestingly, in the borderline case, where the magnetic field decays just as 1 over r times some coefficient, which I call B0, then the spectrum is dense pure point in the interval from 0 to B0 squared, and absolutely continuous onwards from B0 squared to infinity. So there is a mobility edge at B0 squared where the spectrum changes character from dense pure point into absolutely continuous spectrum. And now, if we put this magnetic field into our setting, so V is equal to 0, that means that omega 1 and omega 0, of course, equal to 0. So our threshold lambda is now equal to beta, so it's beta squared, sorry. So it's lim sup of x times b squared. Then we see that it is our threshold is 0 in case 1, and in that case there are no positive eigenvalues, and it is equal exactly to b0 squared in case 3, so to the mobility edge. Okay, it is, of course, our result is not applicable in case 2, because in that case b tilde is not bounded at infinity, but in case 2 there are eigenvalues everywhere in the essential spectrum, so it's normal that it's not applicable. But the important point that it is that the threshold coincides in the case in the borderline case 3. It coincides with the mobility edge, which shows that not only is the condition optimal, the decay condition on B is optimal, but even the value of lambda is sharp, because we cannot lower it any further. Okay, because the result of Miller and Simon says that below B0 squared, that the spectrum is dense pure point. All right, so this is maybe this might be enough as for some remarks and some propaganda to this result. I will skip now the discussion of Wigner von Neumann, because this is something which is not concerned with magnetic field, and I will jump to some main ingredients of the proof. I will in the main ingredients of the proof, I will only talk about the situation to make it a bit simpler, when lambda is 0, which means that not both, but all beta, omega 0 and omega 1 are 0. Basically what we do is that we use a modified approach of Fraser and Herbst and Hofmann-Ostenhaus, suitably modified to the situation with the magnetic field, and modified in the sense that we use it in the settings of quadratic forms and not of operators. So what is this? How this approach works? The basic idea is to consider the commutator of the Hamiltonian with the generator of dilations in L2 of Rn. This is of course not new. This is something which has been used many times. I recall that the generator of of dilations is this operator, and it turns out that in our, since we use the Poincare gauge, where A times X is equal to 0, this is just the same as the generator of magnetic dilation. So we can also add the A here. It doesn't change anything on this. And the basic idea is now to calculate the commutator of the Hamiltonian with this operator as a quadratic form, but not as a quadratic form on the potential eigenfunctions, but on the weighted eigenfunctions. Now the eigenfunctions will be weighted with an exponential function, where in the exponential we will have some function f, which is smooth, radial, and bounded, and satisfies these assumptions. So the gradient of f is equal to x times some scalar field g, which has to decay, which has to be smooth and decay sufficiently fast to 0. And now we assume that we have an eigenfunction, which we call the weak eigenfunction, not necessarily eigenfunction is in a classical sense, but the weak eigenfunctions which satisfy this equality. And we calculate the commutator of the Hamiltonian H with this operator D as a quadratic form evaluated on the weighted eigenfunction. Okay, so psi f is the abbreviation of e to the f times psi, and we calculate the quadratic form associated to the commutator of H. I skip now the indices A and V for simplicity. So H is our old operator H, although there is no A and V here. H, I calculate the commutator HD as the quadratic form applied on this weighted eigenfunction psi. Now, what I get is, so the basic idea is that we can calculate it in two different ways. In one way, we use the fact that psi is an eigenfunction of H, or weak eigenfunction, and in the other way, we don't use it. We pretend not to know it, and we just calculate the commutator as it is, and we get two different results. This one and this one. Okay, and this is basically the core, the whole core of this method, because we will now compare these two results to obtain possibly a contradiction when E is either positive or large enough. Now, why should we obtain contradiction from these two results? This is not clear from this math which is written here. However, to anticipate this, we might think of these terms. So these terms that I just highlighted, they have a sign. Yeah, E is, when it's positive, it has a sign. This is a square. This is also a square. And on the other side, this also has a sign, but it has a negative sign, right? And all the rest, we can think about something which under sufficient conditions on B and V, if we choose F in a clever way, it might go to 0. And so these will be the correction terms. And then, of course, we will arrive at a contradiction if E is positive. Okay. So this is more or less how the method works. Now, to be a little bit more precise, let me state one more. Let me show one more basic ingredient of the proof, and this ingredient is included in the following lemma. And the lemma says basically, it says the following thing. If psi is an eigenfunction of H, and if the eigenvalue associated to this eigenfunction is larger than lambda, than our threshold, then this eigenfunction decays extremely fast at infinity. It decays super exponentially fast, okay? In the sense that we can multiply it by the exponential of mu. Mu is a constant, is any positive constant. This x in this bracket with lambda is a generalization of the Japanese x, okay? So I recall the Japanese x would be the x, this one with lambda equal to 1. We have here any parameter lambda. And the result says that if we have an eigenfunction associated to a positive eigenvalue E, or in general larger than lambda, then the associated eigenfunction decays so fast that it stays in L2, even if we multiply it by E to the lambda times this Japanese x, multiplied by any constant mu. Okay, and this is one of the central point of the proof, which means, of course, it does not include eigenfunctions which are connected to eigenvalue 0, because there we know that the decay is not exponential but is power-like. But as soon as the eigenvalue is positive, the eigenfunction must decay extremely fast, so fast that I repeat, it remains in L2, even if I multiply it by E to any constant times x, basically, right, or norm of x. And since this is one of the most important keys of the proof, let me just sketch an idea how this follows. So, of course, it suffices to prove this for lambda equal to 1. And the proof basically goes by contradiction. Yeah. So if we suppose that the sup of all mu's for which this function remains L2 is finite, then we want to arrive at the contradiction, because what we want to prove, what this says, is that this supremum is infinite, right? So if we suppose that by contradiction that the sup is finite, then we can construct a sequence of bounded, smooth, and radial weight functions fk, which satisfy all the properties that I mentioned on the previous slides, and such that the L2 norm, if I don't write L2 norm, then if I write just the norm, then this is by default, it supposes that the norm is an L2 norm, right? And such that the L2 norm of e to the power fk times psi tends to infinity as k goes to 0, right? And now, so I normalize this function in L2, which means I take it and I divided it by its L2 norm, and I obtain a sequence of functions phi k, which have L2 norm 1, all of them, but they will decay to 0 locally because of this property. Okay, they will decay in 0 locally, precisely in H1 norm. So on any compact set, each H1 norm will tend to 0. Okay. And now I plug it in these two identities for the weighted commutator, but instead of psi of f, I just plug in the function phi k, my sequence phi k that I constructed in this way. So I recall that its norm is 1, it's normalized to 1 in L2, and I plug this in, and I just copied all the results. And the point is that since I assume now that b tilde goes to 0, x times v1 goes to 0, and x dot grad v2 goes to 0, and phi k goes locally to 0 in the H1 norm, so in particular in any LP norm larger than 2 or equal to 2, all these terms will disappear as k goes to infinity, right? Well, this one will not really disappear, but this one, because there is p minus a, but p minus a can be also always controlled by this one, which is positive, so you can sort of complete a square. And the same on the other expression. Here, there is something which is clearly negative or non-positive, and the rest will disappear when k goes to infinity. So what I obtain at the end from the first term, only e, I will leave only e. This is positive, but I will throw it away. So on one hand, the commutator is largely equal to e plus something which goes to 0. On the other hand, it is equal to something which is clearly negative plus something which goes to 0. And this is, of course, in contradiction if e is positive. Okay. And so in this way, I can prove that the eigenfunctions decay is extremely fast. And once I have proven this, the rest is more or less simple, because now, okay, I construct a family of weight functions which depend on 3 parameters, mu, epsilon, and lambda, in this way. I do this thing because I need the weight function to be bounded, and I need its gradient to be bounded. So I cannot really use the Japanese x, because Japanese x is not bounded. But I approximate it by this family. And the approximation is in the sense that when epsilon goes to 0, then this weight function tends to the Japanese x multiplied by mu, where mu is a positive constant. Okay. And now I plug it in again into these 2 identities for the weighted commutator. And I let, first of all, epsilon go to 0. And if I do that, I obtain this inequality. I obtain an inequality with a constant which is independent of epsilon, mu, and lambda, where on the one hand, I have L2 norm squared of this function, which I know that is finite because I know that psi decays super exponentially. And on the other hand, I have mu squared times this, right? I have this scalar product. And now I let lambda tend to 0. If I let lambda go to 0, then this will just converge to 1. And I obtain this inequality, which is supposed to hold for any mu which is positive, and which is, of course, impossible unless psi is equal to 0. So this shows that the only function which can be an eigenfunction with this fast decay at infinity is a 0 eigenfunction, and therefore there are no positive eigenvalues. Okay. Just a small remark, with which I will conclude. The proof cannot be extended to eigenvalue 0, of course, because if I take here equal to 0, then this will not be in contradiction, because this quantity will also go to 0. So the proof cannot be extended to 0 eigenvalue, and also the result cannot be extended to 0 eigenvalue, because I know that this operator can have 0 eigenvalue. This follows trivially from the Aharonov-Kashev theorem. If I put myself into the 2-dimensional case, I know that this operator H AB is one of the components of the Pauli operator, and if I take B negative, let's say, and such that its integral is smaller than, oh, sorry, this is also a misprint. This should be minus 2 pi, okay? I'm sorry. This thing should be minus 2 pi, okay? Then the Aharonov-Kasher theorem says that 0 is an eigenvalue of this operator. And in this situation, we of course have lambda equal to 0. So the result, the proof and the result cannot be extended to eigenvalue 0. And the reason behind this is, as I said, the eigenfunctions associated to eigenvalue 0, they do not decay exponentially, but they only have a power-like decay. And of course, in that case, the whole technique does not work. So here I only listed some, not some, but all the papers that I mentioned in the talk. So if someone is interested here in the full bibliographic details of the papers mentioned in the talk, you can consult this list. And I think this is the good time to stop. Thank you for your attention.